In this lecture, we are going to talk about the Hermitian property of operators. Hermitian property. Hermitian property of operators. Property of operators. Okay. And we know that in quantum mechanics, corresponding to every physical quantity or observable, there is some operator, right? We have already mentioned this in the previous lectures. For example, corresponding to momentum, there is an operator. Corresponding to kinetic energy, there is an operator. Corresponding to total energy, there is operator. There is angular momentum operator, like that. For every measurable physical quantity, there is an operator in quantum mechanics. Okay, so let that operator be a cap, and this a cap corresponds to some physical quantity, and this a cap when act on the wave function psi, okay, a cap psi, you get some value like a psi. This is an eigenvalue equation. Here the eigenvalue is a, and this a, the small a, is the quantity that we are going to measure. Okay, for example, if you are using the momentum operator here, what you are getting here will be the value of the momentum. If you are using the total energy operator here, what you are getting here will be the total energy. So the eigenvalue will be corresponding to the physical quantity um, for which we use the operator. Okay, so we have to consider something here. In quantum mechanics, your operator can be real or imaginary. Do you have any doubt that the operator could be imaginary? Yes, it is possible. You have already seen what is the momentum operator. What was that? H by 2 pi I d by dx. That is a momentum operator in the x direction, right? Linear momentum operator. So there is an I here. So this is imaginary. And also the wave function can also be imaginary in many cases. So in quantum mechanics, this is very normal or very usual that the operator and the wave function can be imaginary. Okay, but we know that this operator actually denotes a measurable physical quantity, and that measurable physical quantity is obtained as the eigenvalue. Therefore, this eigenvalue should be a real number. Okay, real number, because that is the observable this is the measurable physical quantity. The physical quantity cannot be imaginary. The value of the physical quantity cannot be imaginary. Therefore a should be real. Okay, so even if a kia and psi are imaginary, a should be real. So this is very important that a should remain real in this eigenvalue equation. A cap psi is equal to a psi. So this actually puts some restriction in the properties of the operator. If you want to know what is that restriction, we have to do some mathematical steps here. Then you will see what is the restriction that we have to impose on the operator in order to keep this cap small a as a real quantity. Okay, so we will check that. So we already know that a cap psi is equal to a psi, and if we are multiplying this equation, let me call this as equation number 1. If we are multiplying equation number 1 with psi star, okay, psi star, um, and integrating, multiply with psi star and integrating, then we get integral psi star, okay, a cap psi is equal to d, dito is equal to integral uh, a psi star psi, or psi star, right? Or we can write it like integral psi star a cap psi dito is equal to a. Actually it is a constant, so we can take it out of the integral symbol. So it is A integral psi star. Okay. So here we have a new equation. Let me call this as equation number 2. Okay. That is integral psi star a cap psi d2 is equal to A psi star. Okay. Now we can consider some other steps. Let us take the complex conjugate on both sides of equation number 1. Then we can write it like a cap psi star is equal to a psi star, right? Means I am taking the complex conjugate of left hand side and right hand side of equation number 1. So that I can write as a cap star psi star is equal to a star psi star, a star psi star, right? So let me multiply this with the psi and integrate. So multiply with the psi and integrate this one. Let me call this as equation number 3. So integrate equation number 3. Okay, multiply with the sign integrate 3. Then we get integral. Okay, psi a cap a cap star psi star d2 is equal to integral um, a star a star. So we can put a star here, right? Because it's a constant. So a star psi star d2. Okay. So we have a new equation that integral psi a cap star psi star d2 is equal to a star psi integral psi star and d2, and equal to that is equal to um, what is this x a star integral psi star that will be equal to a integral psi star d2. Why I wrote a here? Because we already know that a is an eigenvalue. Eigenvalue means it is the physical quantity corresponding to the operator. Okay, the physical quantity cannot be imaginary, therefore a should be real, therefore a star should be equal to a. That's a condition. Okay, a star should be equal to a. That's why I wrote a psi star ditto, because a is always real. A is always real. Okay, so I can write a integral psi star ditto. Let me write this equation once again. Integral psi a cap star psi star ditto is equal to a integral psi star ditto, and this is equation number 4. Okay, and now we check equation number 4 and equation number 2. So we have a ditto here. Okay, equation number so sorry, I forgot to put detail here. And we have equation number 2 and equation number 4. In the equation number 2 and equation number 4, in the right hand side, we have the same quantity, that is a integral psi star d2. Here also a integral psi star d2. Therefore, the left hand side of equation 2 and 4 should be same, right? So we can write like left hand side of equation 2 is integral psi star. We can write it like integral from 2 and 4. From 2 and 4, we can write like integral psi star a cap psi d2 is equal to the left hand side of the equation number 4, that is equal to integral psi a cap star psi star and d2, right? So we have a new equation, and this new equation we can write like this. If we are writing it in a better way, we can write it like this: integral psi star psi star a cap psi a cap psi. Okay, here a cap is operating over this psi, so let me put this in bracket. Okay, d tau is equal to integral psi a cap star psi star. Here actually a cap star is operating over psi star. Okay, let me put that first. Then that is a cap star psi star, cap star psi star, then psi d tau. Here the order is not a problem because um, we are integrating the whole thing from psi a cap star psi star. Okay, so psi a cap star psi star will be equal to a cap star psi star psi. Okay, that doesn't matter, so we can write it like this. And if you are writing it in a if we are writing it in a better way again, then we can write it like integral a cap star a cap psi a cap psi. I am writing this one. Okay, a cap psi star star psi d tau psi d tau is equal to integral psi star a cap psi d tau a cap psi d tau. So I wrote it in many ways, no problem. You can write it in any way. I just wrote it like this. That's all. And this is a new equation. And here we have a relation like integral a cap psi the whole star psi d tau is equal to integral psi star a cap psi d tau. Okay, and why we got this equation? We got this equation because of the assumption that the eigenvalue a is a real value. Okay, so from that only we got this equation. So if the operator holds this condition, means if the operator a caps it holds the condition that integral a cap psi the whole star psi d tau is equal to integral psi star a cap psi d tau, then we can call this operator as the Hermitian operator. So a cap is a Hermitian operator. So what is the condition for the Hermitian operator? An operator a cap can be called as a Hermitian operator if integral a cap psi star psi d tau is equal to integral psi star a cap psi d tau. Then we can call a cap as a Hermitian operator. Okay, and the psi is an eigenfunction of the operator a cap. And we know that this condition was imposed by the condition that a or eigenvalue should be real. Okay, so I hope now you understood what is meant by a Hermitian operator. If an operator is Hermitian, it will always obey this condition. Okay, now you suppose that you have two operators and two eigenfunctions for the same operator a cap. Our operator is a cap, but we have two eigenfunctions. One eigenfunction is psi and another eigenfunction is phi. Both these are the psi and phi are the eigenfunctions of a cap. Okay, in that case we can write like integral a cap psi star, okay, phi d tau is equal to integral psi star a cap phi d tau a cap phi d tau. Okay, a cap phi d tau. So let me put one bracket here just for knowing that a cap is operating on psi. Okay, so if you have two functions psi and phi, then the condition for Hermitian operator is that integral a cap psi star phi d tau is equal to integral psi star a cap phi d tau. Okay, so you should not mess with this equation. You can just remember this equation like this. Okay, your psi and phi are there. Psi and phi. Here also you have psi and phi. Okay, and here actually the operator in the first part or left hand side, the operator is acting on psi. In the second part, the operator is acting on phi. Okay, and you are giving star to psi, and this is because psi may be complex number. If psi and phi may be complex number, then you have to take star. If both are real functions, then you don't need to worry about the star. If both psi and phi are real functions, if both psi and phi are real functions, how you can write? I will write it in another color. If both psi and phi and a cap, okay, and a cap, psi and phi. Sorry, let me write. If both psi and phi are real functions, and a cap is also real. Okay, ഇതെല്ലാം റിയൽ ആണെന്നുണ്ടെങ്കിൽ then you can write it like integral a cap psi phi d tau is equal to integral psi a cap phi d tau. Okay, so this is the case when all are real. A cap psi and phi are real. Okay, so I hope you understood what is meant by Hermitian operator. Okay, so if an operator a cap is Hermitian when it holds the condition that integral a cap psi star psi d tau is equal to integral psi star a cap psi d tau, or if this a cap has two eigenfunctions psi and phi, then the condition is that integral a cap psi star phi d tau is equal to integral psi star a cap phi d tau. Okay, so this is the case. Now let us understand this with some example. Okay, so let us prove that. Let us prove that. Prove that d square by dx square is a Hermitian operator. D square by dx square is a Hermitian operator. Hermitian operator of the function e raised to minus ix raised to minus ix. Okay, that is what we have to prove. We have to prove that d square by dx square is a Hermitian operator. We are given the function as well. So here a cap is equal to d square by dx square, and psi is equal to e raised to minus ix. So if you want to prove that this is a Hermitian operator, then we have to prove that integral a cap psi the all star psi d tau is equal to integral psi star a cap psi d tau. That is what we have to prove. Okay, so let us first take the left hand side of this equation. So what is the left hand side of this equation? Integral a cap psi the whole star psi d tau, and that is equal to, in our case, that is equal to integral a cap is d square by dx square of psi is equal to e raised to minus ix. Okay, the whole star into psi d tau, that is e raised to minus ix. D tau in this case is dx because we have only one variable here, that is x. Okay, and now let us see what is the result of this one, and that is equal to integral d square by dx square of e raised to minus ix, that is equal to d by dx of the first derivative of e raised to minus ix, that is equal to e raised to minus ix multiplied by the coefficient of x, that is equal to minus i into e raised to minus ix. Okay, star e raised to minus ix dx and that is equal to integral uh, d by dx of e raised to minus I into e raised to minus ix. Okay, so we can take minus I out of this differential sign because that is a constant. So let us put minus I here, minus I into d by ds of e raised to minus ix, that is equal to minus I e raised to minus ix. So this will be minus I into minus I. Okay, so that is equal to plus I square. Okay, then e raised to minus I x into what is remaining, that is the star of this one. Okay, star e raised to minus I x dx, and that is equal to integral what is minus I square, that what is I square, that I square is equal to minus 1. So let us put minus sign here. So minus integral e raised to minus ix star. Okay, minus ix star is equal to plus ix. So it is e raised to ix into e raised to minus ix dx, and that is equal to minus minus integral e raised to ix into e raised to minus ix, that is equal to 1. So dx, that is equal to minus x. Okay, so that's the result. So that is the result of the left hand side. Now let us take the right hand side. Right hand side is integral psi star a cap psi d tau. Integral psi star a cap psi d tau. Integral psi star a cap psi d tau. Okay, we will evaluate this one. So that is equal to integral psi star. Psi star in our case is e raised to ix, not e raised to minus ix, because we are taking the complex conjugate. So that is equal to e raised to ix into a cap psi d tau, that is equal to d square by dx square of e raised to minus ix, e raised to minus ix dx. Okay, and that is equal to integral e raised to ix into d by dx of minus I e raised to minus ix. Okay, dx, that is equal to integral e raised to ix d by dx of minus I e raised to minus ix, that is equal to I square, that is equal to minus 1. So I can write I square e raised to minus ix dx, that is equal to minus integral e raised to ix e raised to minus ix dx, that is equal to minus x, right? Minus x. So right hand side is also equal to minus x. Left hand side is also equal to minus x. What does it mean? We have proven that. Thus, we have proven that a cap psi star psi d tau is equal to psi star a cap psi d tau. This equation is proven, right? So if this equation, if the operator holds this condition, then we can call a cap as a Hermitian operator. Therefore, what is the result? D square by dx square is a Hermitian operator, right? D square by dx square is a Hermitian operator. Okay, it is a Hermitian operator. We have proven that. So with this example, I hope you got what is meant by Hermitian operator. And we can now take an example of two eigenfunctions. Okay, two eigenfunctions. So what is the eigenfunction here? Here the operator is same, d square by dx square. Let's take a cap is equal to the second example. Okay, this is second example. A cap is equal to d square by dx square, and we have two functions. Psi is equal to e raised to ix, and phi is equal to sin x, and phi is equal to sin x. Okay, we have two functions here, and now we have to prove that a cap is a Hermitian operator. Prove that d square by dx square is a Hermitian operator. If it has to hold the condition that d square by dx square is a Hermitian operator, then we have to prove that this one with the two functions. We have an equation here. What is that? Integral a cap psi star phi d tau is equal to integral psi star a cap phi d tau. Let me take this equation from here. This equation, okay? So integral. So this equation. Okay, let me take this equation from here and put it here, and we are going to prove that this equation valid in this case also. So let me take it here. Okay, we are going to prove that this equation is valid here. So in our case, a cap is equal to d square by dx square. So let us take the left hand side of the equation, LHS. Okay, left hand side of the equation, LHS. LHS is integral a cap psi star, okay, phi d tau, that is equal to integral a cap psi. What is a cap psi? D square by dx square of psi. Psi in our case is e raised to ix. E raised to ix, the whole star, okay, star phi d tau. Phi in our case is sin x. So let me write it as sin x dx. Okay, so that is equal to integral d square by dx square of e raised to ix. What is that? That is d by dx of first derivative of e raised to ix. That is equal to I e raised to ix. Okay, so star sin x dx, and that is equal to integral d by dx of this quantity, that is I into I square, that is I square into d by dx of e raised to I square into e raised to ix. Okay, e raised to ix into that is the star of that one. Okay, into sin x dx, but I square is equal to minus 1, so we can take it like a minus integral e raised to ix, but we have to take the complex conjugate of this one, so we have to write e raised to minus ix sin x dx. Okay, so our result is integral integral e raised to minus ix sin x dx. Okay, that is equal to left hand side. Now we can take the right hand side, RHS, right hand side. What is RHS? Integral psi star a cap phi d tau. Okay, so that we have to take integral psi star a cap phi d tau, that is equal to integral psi star in our case is e raised to ix, right? E raised to psi in our case is e raised to ix, therefore psi star is equal to e raised to minus ix, that is psi star. Then a cap is d square by dx square of sin x dx. Okay, that is equal to integral e raised to minus ix d square by dx square of sin x, that is equal to d by dx of sin x is equal to cos x, and again we are taking the derivative of that one, cos x, then we get a minus sin x, right? So we have to write minus sin x dx, that is equal to minus integral e raised to minus ix sin x dx. Now you check the right hand side, the result of left hand side and right hand side. This is the left hand side, minus integral e raised to minus ix sin x dx. What is the result of right hand side? Minus integral e raised to minus ix sin x dx. Both are same, right? Therefore you can write it like left hand side is equal to LHS equal to RHS. So we have proven that integral a cap psi whole star phi d tau is equal to integral psi star a cap phi d tau. We have proven this. So what does it mean? D square by d square is a Hermitian operator. Therefore, d square by dx square is a Hermitian operator. Okay, so with these two examples, I hope you understood what is meant by Hermitian operators. Okay, this is very important in quantum mechanics, and from this one, we have proven that all quantum mechanical operators must be Hermitian operators. Okay, why it should be so? Because in quantum mechanics, the operator actually represents some physical quantity, and the eigenvalue of that operator should be the physical quantity for which the operator is corresponding to. So if you are using the momentum operator, the eigenvalue will be the momentum. If you are using kinetic energy operator, the eigenvalue will be kinetic energy. So momentum, kinetic energy, total energy, position, whatever it may be, all these are real quantities and cannot be imaginary. Therefore, the eigenvalue must be real. If the eigenvalue is real, it should hold this condition. We have already proven that. So, if this condition is if the operator is holding this condition, then we can call this as a Hermitian operator. Or in other words, we can say that all quantum mechanical operators are Hermitian operator. Let me write it here. All quantum mechanical operators, all quantum mechanical operators operators are Hermitian operators. I hope you understood what is meant by Hermitian operator and what is its important in quantum mechanics. If you have any doubt, please don't hesitate to ask me. I am ready to help you. And as I always say, you have to keep your notebook with you. Okay, that is written here. Please write notes in a book while watching this lecture for a better understanding or better experience. Pause the video wherever you feel difficulty to understand the concept before proceeding further. So you have to do this always. Keep a notebook for the quantum mechanics, and whenever you watch this lecture, you have to keep notes in your notebook. Okay, and thank you for watching. I hope you understood uh, the basics of Hermitian operators, why it is important in quantum mechanics. And thank you for watching and stay tuned.